Hello, and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 3rd, 2025, and we're diving into some cool graph research. We'll be discussing this ICLR conference paper, published just over 3 months ago on January 22nd, called Joint Graph Rewiring and Feature Denoising via Spectral Resonance. Essentially, it tackles noisy graph data, messy connections and features, proposing a method to jointly clean up both the structure and features by aligning their spectral information. Alright, so let's look at how this JDR method works visually. This schematic starts with a noisy graph on the left. Its connections and features aren't really aligned with the node classes. The process involves taking the graph's adjacency matrix A and feature matrix X, performing spectral decomposition, then iteratively refining and combining their spectral information. The result, shown on the right, is a cleaned-up graph with better community structure and clearer features. Okay, so now let's see how JDR stacks up against other approaches. This table compares it with methods like DIGL, FOSR, and BORF. What stands out is that JDR is the only one here that explicitly uses node features for rewiring, aligning with that spectral resonance idea we discussed. It handles both adding and removing edges, works for heterophilic graphs, and maintains a pretty efficient ON complexity per iteration. Moving to the results, this figure shows test accuracy using synthetic graphs generated by something called the Contextual Stochastic Block Model, or CSBM. The x-axis varies the graph type from heterophilic, meaning nodes tend to connect to dissimilar nodes, to homophilic. You can clearly see that applying JDR. The red and yellow lines significantly boost the accuracy for both GCN and GPR-GNN across this entire spectrum, compared to running them without JDR. Okay, so we saw JDR works well on synthetic data, but how about real-world graphs? This table shows results specifically on heterophilic datasets, like chameleon, squirrel, and actor. Again, it compares GCN and GPR-GNN with and without JDR and other preprocessing methods. Well, the JDR rows, GCN plus JDR and GPR-GNN plus JDR, consistently show the best or near best accuracy highlighted in bold. This really reinforces that JDR significantly helps, especially on these tougher, heterophilic graphs. So we just saw JDR shine on heterophilic graphs. Now this table shifts focus to homophilic datasets like Quora, CiteSeer, and PubMed. And, well, the story is quite similar. If you look at the bolded numbers, JDR combined with GCN or GPR-GNN again consistently achieves top performance across these datasets. It really shows the broad applicability of jointly denoising the structure and features, not just for tricky graphs. Okay, and this pattern of improvement holds even for larger graphs. This table, Table 4, specifically looks at bigger datasets. Questions, Pen94, and Twitch gamers. You can see they have tens or hundreds of thousands of nodes and millions of edges. Well, even at this scale, applying JDR to GCN, that bottom row, consistently delivers the best accuracy across all three, shown again in bold. It really demonstrates the method scales effectively. Alright, so we've seen JDR works well even on large graphs. Now, this figure 9, really digs into why it might be so effective. It plots that spectral alignment metric we discussed earlier, comparing JDR with other methods on real-world datasets. Well, across both homophilic and heterophilic graphs, you see the JDR bars in brown consistently achieve the highest alignment. This directly shows JDR successfully maximizes that spectral resonance. So that spectral alignment improvement really seems key. Wrapping up, the core idea here is that by jointly denoising graph structure and node features, guided by this principle of spectral resonance, JDR significantly cleans up the data. And as we saw across many experiments, this leads to consistently better performance for downstream GNNs on various tasks and graph types. It really suggests tackling noise directly is crucial. All right, that's all for this research roundup. Thanks for joining.